All right, so in this video, we are going to discuss uh, graphing trigonometric functions. We're going to mostly talk about sine, cosine, and tangent, and then look at an application of one of those trig functions. Okay, so let's go back to the unit circle. This is the main way we found values of trig functions. And so how did we find the sine of, let's say, 30 degrees if we use the unit circle? Well, one way that we did this was we said sine can be thought of as y divided by r. If you think of a triangle in the first quadrant, then we label this y, this is r, and another way is opposite over hypotenuse, right? But y over r. And if you're using the unit circle, we said that this is y divided by 1, because r, the radius of the unit circle, is 1. And so you could really just call this the y coordinate. And so the sine of 30 degrees, if 30 degrees is this one here, then the sine of 30 degrees is 1/2. Okay, so the cosine of 30 degrees is right there, the square root of 3 over 2. But in this section, we're going to focus on just the sine of various angles. And we're actually going to look at the sine of a lot of these popular angles from 0 to 2 pi radians. So we'll just, maybe draw out a couple here. The sine of pi over 6 is, we just said, 1/2. So that's there. We're making essentially an XY chart, or a T, sine of T chart. I skipped one here. The sine of 0 is 0. The sine of pi over 4 radians is square root of 2 over 2. Sine of pi over 3 is square root of 3 over 2. And then the sine of pi over 2, or 90 degrees, is 1. So we continue this, and we can see that actually the sine goes back to the square root of 3 over 2 when the angle is 2 pi over 3. Then again, it goes back to the square root of 2 over 2 when the angle is 3 pi over 4 radians. Then back to 1/2 again. And then the sine becomes 0 at pi radians. And so if you continue to go around this unit circle, we can create this table for what we call one period of sine. And we can then take this chart of values and graph it on the, XY plane, or the T sine of T plane. And we notice that it looks like the maximum value occurs at, and actually let me use a different color here, at pi over 2 radians, and the maximum value that occurs is 1, and that's right here. And we can go through and say, okay, sine starts at 0, 0, the origin, and then we said for an angle of pi over 6, we're at a height of 1/2. We'll say that this is pi over 6 radians, and so on, right? We can go through all of these. The value is increasing up until pi over 2, and then you saw that the value started to repeat. So that means if it was increasing before, the value is then decreasing afterwards, and then it starts, or it continues to decrease, and then it begins to increase and goes back to the value of 0 at 2 pi radians. And then it would repeat again, right? Because we said the sine of coterminal angles would be equal. And so this thing will then repeat, in a periodic fashion. Okay, so let's talk about some of the characteristics of the sine function. And all of this is actually from the textbook. So, you're welcome to take a look at the textbook. Just screenshot it there. So a couple of notes here. We'll talk about them for sine. The domain is all real numbers. you can take the sine of any angle. The range is from -1 to +1. We can see we said that the maximum value was +1. It occurred at pi/2. The minimum value is actually -1, if you take a look at that. Oops. And it occurs at 3 pi/2. And again, these will occur, again at other, locations, but this is mostly for um, the first period, right? That I'm talking about, this period that we're looking at. So what is a period? One period is, once the function starts to repeat again. And so the period is 2 pi radians. And after 2 pi, the behavior would be, identical to the previous period. Of course, this period can be changed. The length of a period can be changed if you were to stretch this or compress this horizontally. We talked about transformations earlier in this class. And so you know of, horizontal stretches and compressions, which can change the length of a period. The period can be 1 pi or 4 pi or any other, value. Okay, we actually already talked about the maximum value. We said that the maximum value of the sine of t is 1. And we said it occurs here at pi/2 radians. But then since the period is 2 pi, we can just add 2 pi to this, and we would get another maximum. And really, we can add a multiple, 2 pi times k, because 2 pi plus 2 pi radians later, it will reach another maximum. But the maximum is 1. Same thing for the minimum. We have a minimum of -1. And then maybe this is interesting here, the zeros, where does this sine function equal 0 or have a value of 0? And that would be at these locations here, at 0, at pi, we can see that from the graph, and at 2 pi. And what we notice about all of these zeros is they are a multiple of pi, 0 pi, 1 pi, 2 pi, 3 pi, and so on. So we can say the zeros occur at k pi, where k is some integer. Okay, so just multiples of pi, basically. All right. So let's, we got a couple of basic characteristics. Let's go ahead and move on to an example problem. All the problems that we go over in this video are going to be similar to some of the problems that we do in the worksheet. Okay, so we could do the same thing for cosine as well. It would be very easy to, do this for the cosine graph. And so, this is done. What we'll say, though, just to give some basic characteristics of the cosine graph, is that the cosine starts off up here at +1, and then it decreases and reaches the value of 0, continues to decrease, reaching its minimum value of -1, and then starts to increase, again has another 0, reaches its maximum value after increasing some more, and then it will repeat another cycle. And so it's a good idea to know, excuse me, it's a good idea to know just the basic shape of the graph. Okay, then later when we graph these, we're going to transform this basic parent function. So cosine starts at a maximum and decreases to a 0. Then it decreases to its minimum, increases to another 0, and then increases to its maximum to repeat again. Okay, and just to point out the behavior of the sine function, let's go ahead and just point that out really quick. Sine starts at the origin, or 0, at its 0, increases to its maximum, decreases to a 0, decreases to its minimum, and then increases to a 0 where it resets again. It starts all over. Okay, so let's go ahead and take a look at some of the characteristics of pi, some of the characteristics of cosine, and we'll go through just a couple of these here. I won't talk about them in detail, but the domain is all real numbers. The range is also -1 to +1. And then one of the important ones here that I want to point out is the period is 2 pi if it isn't stretched or compressed horizontally. The period is 2 pi. And so we can break up a period by looking at, from 0 to 2 pi. This is the length of a normal period. And since we have 4 sections here, we have 4 sections, right? I have colored them in green, blue, orange, and yellow. We can actually take the period length, which is 2 pi in length, and divide it by 4. Divide it by the number of sections, which is 4. And so this gives us that each of these sections will be length pi over 2 if we're reduced by a factor of 2. So every pi over 2 radians, something special is happening, right? At 0, it has its maximum for cosine. And then at pi over 2 radians later, I am using this number here, pi over 2 radians later, we reach a 0. Pi over 2 radians later, we reach a minimum. Pi over 2 radians later, we reach another 0. And then pi over 2 radians later, we reach a maximum and we start all over. Okay, so this is kind of the idea that we're going to use to graph cosine. All right. We'll go ahead and move on, and then we'll talk about tangent in a little bit. This is already kind of a lot of information, sine and cosine. It might be a review for you, so if it is, that's good. If it isn't, yeah, then we'll move on and we'll come back to tangent after doing a few problems. Okay, so here is a graph of a function, and we want to figure out what function this is. This is just a screenshot from the textbook, one of the problems there. And so let's go ahead and figure out which of these functions is graphed here and write the equation for this function. So the first thing that we should notice is this thing starts at a maximum. And that tells us that this function could be cosine, right? And so for right now, I'm going to call it cosine of x. And so we can look at what is, the length of one period here. Where does this thing restart? Remember that cosine, it starts at a maximum, generally, reaches a 0, then its minimum, then another 0, and then its maximum. And so this is the length of one period. So a period for cosine, in this case, is 5 pi radians long. And so this means that it must have been stretched by some factor. So there is actually a formula to calculate the period of cosine and sine. And that formula is 2 pi divided by b, where b is the coefficient in front of x in that trig function. And so if we have 5 pi equals 2 pi over b, we can solve this for b. 5 pi equals 2 pi over b. How do we solve this? Well, let's multiply by b on both sides. And then we'll divide by 5 pi at the same time here. And so b is equal to 2/5. And so this tells us that this function is cosine of 2/5 x. And then this function actually does not go up to +1 and -1, right? It doesn't actually go that high. So that means it must have had a vertical stretch or compression. And so that means that there must be some factor a in front of the cosine that is either stretching this vertically or compressing it vertically. And since this isn't reaching +1 or -1, that means it must have been compressed. And so there must be a factor of a in front of cosine that is between -1 and +1. And so here we're just going to eyeball this one. If there's something like this comes up on a quiz, it'll be fairly clear what the value of a is. In this case, it looks like this would be here. This would be 0.5. So we'll say that this is 0.75 or 3/4. So we have 3/4 cosine of 2/5 x, and this is our function. All right, so this would give us a cosine graph whose, there's actually a word here that will define the amplitude, whose amplitude is 3/4. And this essentially means the amplitude is how high the function goes from this axis down the center of the cosine graph. In this case, it's just the x-axis. So how high or how low this function deviates from that axis. And that is 0.75 or 3/4. And then the period, let's just double check this here. The period is 2 pi divided by b, but we said that b is 2/5. And so 2 pi divided by 2/5 is the same thing as 2 pi times 5/2. And if we multiply this out, we get 5 pi. Oh, and that's exactly what the period is in the graph that was given. Okay, so that boxed function is the correct one. So there's a couple problems like this on the worksheet. Let's take a look at another one. Is this a sine function or is this a cosine function? Well, if we see that it starts at a maximum, then we can say that this is a cosine function. Now, you could technically say that it is a sine function with a horizontal shift. Maybe the sine function starts right here. But we're actually in this worksheet, we don't really talk about the horizontal shift too much. So we'll just call it a cosine function because we can call it that as well. Okay, so the characteristics of cosine are, it starts at a maximum, it has a 0, a minimum, another 0, and then a maximum where one period ends. Okay, if we wanted to draw another period, just because it's kind of clear here, I'm going to put, the start of another period is here, a 0, a minimum, a 0, a maximum, and another period begins. Okay, so how long is one period? Well, let's take a look. So let me write this in green. The period here is, it looks like it's between 2 pi and 3 pi, right in between there. And so if we write these in halves, this would be 4/2 pi, or 6 pi over 2 is 3 pi. So this would be 5 pi over 2 for one period. Period is 5 pi over 2. And the formula for a period of sine or cosine is 2 pi over b. And so we can solve this for b. Again, we'll multiply both sides by b. And at the same time, let's go ahead and divide by 5 pi over 2. 5 pi over 2. And so b is equal to, if all this stuff cancels here, b is equal to 2 pi times the reciprocal of 5 pi over 2, 2 over 5 pi. The pi's cancel and we get 4 over 5. So far, we know that this is a cosine function with a 4/5 there. Okay. What else? We also need the amplitude. And so the amplitude, if we see this axis here, some textbooks call this the sinusoidal axis. It's the axis that goes down the horizontal middle of the function. And so how much does it deviate from there? We'll check right here. What's this length basically right here? This length, it looks like, is, if this is 1.5, since this is 1.5, we'll call this 1.75. So 1.75. This is our function. Now I'm actually curious. I didn't actually think to do this earlier, but let's graph this on Desmos. 1.75 cosine of 4/5 x, and let's verify that this actually gives us, a period of 5 pi over 2. 1.5 cosine of 4/5 x. One 1.5 cosine of 4/5 x. And so we can see, 1.75, I think is what I said. One period seems to end. Oh, there it goes. Yeah, it tells us actually 5 pi over 2, comma 1.75. And that is the coordinates of, the end of one of the periods there. 5 pi over 2, comma 1.75. All right. And if we look at the shape, is that the same shape? Yeah. Yeah, pretty good. Our graph starts right there. Let's see if I can stretch this. All right, does that shape look like, that one in the picture? Yeah, it does. All right, good. Let's go ahead and move on. And we'll do one more here. Let's do this one quickly. And I guess I happened to take screenshots of a bunch of them that were cosine. Again, this one starts at a maximum. So we'll say it's a cosine function. It has a 0, a minimum, a 0, and then it resets here. So how long is a period here? A period is 1/36 of a unit, which is equal to 2 pi over b. And so the value of b, if we multiply by b on both sides, and multiply by 36 on both sides as well, to cancel out this 36 on the left-hand side, b is equal to 72 pi. So far my function is cosine of 72 pi. And I believe all of the answers in the worksheet, really we're just looking for the amplitude and the value of b. So we have b equals 72 pi. Now the value of a is how much deviation we have here. And you can see that yellow mark there is 4 units tall. And you can even go in the negative direction if you like. That is 4 units tall as well. And so we have 4 cosine of 72 pi. All right, very good. Now, in some of the problems, it actually asks us to graph a cosine function. It no longer gives us the graph and tells us to figure out what the actual equation for the function is, but it gives us the equation of a cosine function and tells us to draw So let's go ahead and read this problem here. It says, use a reference rectangle and the rule of fourths to draw an accurate sketch of the following functions through 2 complete cycles, one where t is greater than 0 and one where t is less than 0. Clearly state the amplitude and period as you begin. Okay, and we're not going to do problem number 15. That one's kind of simple. We'll do a couple of other different ones. All right, so let's take a look at y equals 0.8 cosine of 2t. The amplitude is 0.8. The period we said is 2 pi over b. b in this case is 2. And I'm getting that from the coefficient there I just highlighted. That's these 2 values. So this is a period of pi radians. And so remember the rule of fourths. That's kind of what we talked about earlier. And we said, okay, well, one way to do this is actually, let's see here. Let's mark these as 0.2, 0.4, 0.6, and 0.8. We'll go in the negative direction, negative 0.2, negative 0.4, negative 0.6, and negative 0.8. That is the amplitude. So that's how high and how low we're going to go. Of course, this could also be vertically shifted. You know, we can see vertical shifts. You know, if we had like a -7, then this would shift the graph down 7 units and our graph would look a little different. But in this case, there's no vertical shift. So here we've set up the vertical axis for our amplitude. The period is pi radians. So remember that we said something special happens every quarter, right? We can break down the cosine function to 4 pieces. And so what we can do is we can take the period and divide it by 4 to find the increment in which one of those special things will happen. Okay, so let me go ahead and take my period, pi, and divide it by 4. And we get pi over 4 radians. And so that means that my horizontal axis should be divided into pi over 4, 2 pi over 4, 3 pi over 4, and then 4 pi over 4. Okay, and this is going to be very squished in a sense when I graph this, but that's okay. They want, in this problem, I believe on the worksheet, it only asks us to draw a single cycle. This in the worksheet asks us to draw 2 complete cycles. So we'll do 2 complete cycles, but we really, for the worksheet, only need to know how to do 1. So we have to ask ourselves, where does cosine start? Right, it starts at a maximum. So I'm going to draw nice and big dots there. And then at the next special value, it has a a 0. Then at the next special value, 2 pi over 4 or pi over 2, it has its minimum value. Then it goes back up to its 0. And then finally, it's going to restart here. And so our function is going to look something like this. And then why not? Let's go ahead and just. If we just continue to draw these, look something like that. We wanted at least in the textbook, they ask us where we want a period where t is less than 0 or t is negative. And so I'll draw that in purple, and that would just go in the other direction. Now this little graph paper that they gave was not really the best, but you can get the idea there of this. This is just a little rough sketch. Okay, so these values in the negative direction would be negative pi over 4. I'll reduce here in the negative direction. So this is negative pi over 2 or negative 2 pi over 4, negative 3 pi over 4, and then negative 4 pi over 4 or negative pi. And we can see that the period is pi radians because, here's another one. It goes from pi to 0, negative pi, excuse me, to 0, and that length is pi. All right, nice. Let's try another one. Maybe for this one, I'll only graph a single period. So let's find the amplitude. The amplitude, it's pretty easy. It's just the absolute value of this number here. If it had been a negative 4 in front of there, the amplitude would still be positive 4. Take the absolute value, so maybe I'll write absolute value of 4, which is just 4. The period is 2 pi over b. In this case, b is 5 pi over 3, kind of a fraction there. So 2 pi divided by 5 pi over 3. So this is 2 pi over 1 times 3 over 5 pi, which, if these pi's cancel, gives us 6 over 5. Okay, period is 6/5 of a unit. Nice. So, what are my increments going to be in the horizontal axis? Remember, I take the period and I divide it by 4. So the period number 6 over 5 divided by 4, or we can call that 4 over 1. So that's 6 over 5 times 1 over 4. If we reduce by a factor of 2, we get 3/10. Okay, so 3/10 is the increment that we're going to use in the horizontal axis. And I'll use, let's go ahead and use 2 tick marks to represent 3/10. I'm only going to do one period in the positive direction because I won't have enough tick marks in the negative direction. 6/10. Of course, we could reduce these, 9/10, and 3/10 more would give us 12/10. All right, the amplitude of 4 means we should go 1, 2, 3, 4. This time we'll give them whole unit designations in the vertical direction. -1, -2, -3, and -4. So the most important points here are, these special points, the maximum, the 0, the minimum, the 0, and a maximum to complete the cycle. Just bump that up there. And here we go. It's going to look something like this. I'll just graph a little portion. And my, let's see, graph is just a little sloppy right now. But these are sketches here. All right, and then let me just cut a little piece off here. There we go. That's one period. All right. Very good. So we've graphed a sine function. Whoa. Little mistake there. what I just graphed is cosine, right? Because cosine starts at a maximum. So let me draw this in blue for cosine of 5 pi over 3. T is the one that I just graphed. Let's call it f of x. Now sine is different. I actually, when I was choosing these problems, I wanted to choose one sine and one cosine. So a lot of the work is actually very similar. It's almost the same, except since we're graphing sine here, I'll circle this in purple, and I'll graph it in purple. The increments in the horizontal direction are still going to be the same. The amplitude is still going to be 4. The period is still 6/5. So let's just graph sine properly. Sine, remember, starts at its 0. It reaches its maximum at that first, special value on the horizontal axis. It then gets a 0 again, then reaches a minimum, and then goes back to 0 again. Okay, so here is our sine function. There we go. All right. And so actually we graphed a sine and a cosine on that one. The one we were supposed to graph was sine. And so there it is in purple. All right, so make sure you essentially memorize what this function looks like. Cosine starts at a maximum, right? And that's what I was graphing first. Sine starts at a 0 and increases, decreases, and so on. Right, it always reaches a special point is what I'm calling them right now, which is either I'm talking about a maximum, a 0, a minimum, and then that's it, or 0, right? All right. So let's talk about tangent then. Tangent we can find because tangent is defined to be y over x, right? And so if we find the y value and divide it by the x value, the values of sine divided by the values of cosine, we can divide those and we get the value of tangent. So basically just put in the tables together for sine and cosine, we can find values of tangent. So I'm not actually going to walk through them. I'm going to give a couple of special points here, and they are, let's see here. What happens at pi over 2? Sine has a value of 1, cosine has a value of 0, so tangent is 1 divided by 0, which is undefined. And so we can see that at pi over 2, we have a vertical asymptote, and the tangent function is not defined there. Okay. This actually does occur at negative pi over 2 as well. Tangent is undefined. And we could actually see this by looking right here. There's another vertical asymptote. Okay. And so it turns out that a period of tangent is from negative pi over 2 to pi over 2. This is the one that I like to graph. Negative pi over 2 to pi over 2. And these should actually be round parentheses rather than square brackets because the vertical asymptotes means that the function is not defined at negative pi over 2 or positive pi over 2. Now we can see if we read this from left to right, the function is increasing from left to right. And a couple of points to note is this one here, whose coordinates are pi over 4 comma 1. And why is this, a special point, pi over 4 comma 1? Because at pi over 4, it turns out, go look at the unit circle. The value of sine is the same as the value of cosine. If sine and cosine have the same value, then tangent is just going to have a value of 1. Now, if we go to, let me scroll up to the unit circle and look at 7 pi over 4, or call it negative pi over 4, they're coterminal to each other, the tangent of negative pi over 4, or the tangent of 7 pi over 4, is y over x. This is just negative 1. And so the tangent of negative pi over 4, and let's suppose I drew that correctly, the y value there would be negative 1. And so these are some special characteristics of tangent. Another one is the 0. The 0 of tangent is just at the origin, 0, 0. So again, we can break this up into 4 sections in a sense. We have an asymptote at negative pi over 2. Then it increases to get to its, this point, negative pi over 4, comma, negative 1. It gets to its 0. Then it increases some more, gets to pi over 4, comma, 1. And then it increases, and then you essentially, draw your second vertical asymptote, and that is 1 period of tangent. And so you can see, hopefully you can see that the difference between these two is pi radians. Pi over 2 minus a negative pi over 2 is pi. And so some characteristics. What is the domain of tangent? It is all values except the vertical asymptotes. So except pi over 2, which is the vertical asymptote highlighted in yellow. The period of tangent is pi radians. So we add some multiple of pi. If you add negative 1 pi, it puts you over here at the orange vertical asymptote. If you add 1 pi, it puts you over here, and we see we have another vertical asymptote. Okay, so there are infinitely many vertical asymptotes. The range of this function here is all real numbers, since it goes down to negative infinity and up to positive infinity. The asymptotes occur exactly where the domain is, at the values at which the function is not defined. The period we already mentioned is pi. More generally, if there's a vertical or horizontal stretch or compression, then the period can be found by doing pi over b. Yeah, and then this function is an increasing function from left to right. All right, so let's go ahead and take a look at, do we have an example of one of these? I believe we're just going to jump in and graph one. So let's go ahead and graph this. And it says graph each function over the interval indicated, noting the period, asymptotes, zeros, and value of a and b. Okay. So in this case, Vs is going to be for a vertical stretch factor. That's going to be kind of like the amplitude in a sense. You'll find in the same area. In this case, this is going to be 1. The period is now going to be pi divided by b. And in this case, pi divided by b is pi divided by 2. So a period is pi over 2 units long. All right, so in this problem here, we're asked to graph from negative pi over 2 to positive pi over 2. So let's go ahead and divide this pi over 2 by 4. Again, we're going to break this up into 4 sections. Pi over 2 divided by 4. What does this give us? Pi over 2 times 1 over 4, which is pi over 8. And this is the increment in which we're going to be working. We can start at 0. And let's go ahead and add pi over 8 to each of these increments. So this is pi over 8 here. Then we have 2 pi over 8, 3 pi over 8, and then 4 pi over 8. If we reduce 4 pi over 8, that is really pi over 2. In the negative direction, we get the same thing, negative pi over 2, negative pi over 8, negative 2 pi over 8, negative 3 pi over 8, and negative 4 pi over 8. And so what do we get here? Remember that a period is going to be pi over 2 radians long. Now, what was the behavior of the tangent function? If we take a look at it, it has a 0 at the origin. Now, our function is going to be compressed horizontally, but we'll still have that 0 at the origin. And so let's go ahead and sketch our graph. It will have a 0 here. And let me go ahead and use 2 tick marks to represent a value of 1. And so 2 tick marks in the negative direction will give us negative 1. And so if we have our 0 at the origin, then at pi over 8, we're going to have a value of positive 1. And at the next pi over 8 interval, or increment, 2 pi over 8, this is where we'll have our vertical asymptote. The same thing goes in the negative direction. We will have negative 1 here at negative pi over 8, and then a vertical asymptote here at negative 2 pi over 8. All right, so we're ready to sketch. And remember, we follow the vertical asymptote, so it's going to be coming rising out of the vertical asymptote, and then approaching the second vertical asymptote. And I'll put an arrow on this end. Okay, so if we want to graph all the way from negative pi over 2 to positive pi over 2, here's one period. We're done with one period, but in this textbook problem, it asks us to graph, over this entire interval. Well, then that means that we're going to have, we'll just repeat the process here. Since we only have about half of this graph, paper left, the rest of it's going to look like this, like that. And of course, it would continue if we went to the left, if we had more graph paper. And then we're going to have this behavior. And we would have a 0 here, and it would continue. Might as well, since we have the space on this side, let's go ahead and graph it just really quickly. Okay, it looks like that. Okay, so there's 2.5 periods of tangent. All right. Now, to make sure we've done this, correctly, we actually could plug in all of these values if we wanted to, if we didn't want to use, these ideas that I'm giving here, the function transformations. But let's just say we wanted to plug in. We said, well, what does this, is that actually a point on this graph? Is it 0, 0? Well, we could say, well, what is the tangent of, we plug in 0. And so we would get the tangent of 2 times 0 is 2 times 0 is 0. And what's the tangent of 0? That's 0. So we get the point 0, 0. We could plug in a bunch of points into this, but that would be a lot of work. And so if we just understand the basic shape of tangent, sine, or cosine, figure out how long a period is, remember the basic shape of the parent function, and then we can graph. That saves a little bit of time. All right, so we'll take a look at one more. Oh yeah, this video is getting a little bit long. Just to kind of give us another example, it takes practice to do these problems here. So, after watching this, hopefully you'll practice. Maybe you might even have to re-watch the video. But you want to watch a section like on sines, how to graph sine or cosine, and then do the corresponding problems in the worksheet. All right, in this case, the vertical stretch factor is going to be 3. And I'll put the absolute value of 3, which is 3, I guess. Yeah. If it was negative, then it would just reflect the graph about the x-axis. The period we said is pi over b. In this case, b is what? B is 2 pi. It's the value in front of the variable inside of the function. B is equal to 2 pi. And so we get pi divided by 2 pi. And so this is, if these cancel, we get 1/2. A period is 1/2 unit in length. And so if we divide this by 4, what's 1/2 divided by 4? This is 1/2 times 1 over 4. And this is 1/8. And so we're going to go in eighths in this case. Here we have 1/8. Here we have 2/8. Negative 1/8. Negative 2/8. All right. Let's see. The vertical stretch factor is 3. So instead of having that special point at a height of 1, it's going to go up to positive 3 and negative 3. Okay, and so what does the behavior of tangent look like? If you're using this rule of fourths, meaning finding the period, dividing it by 4, and then for tangent, knowing that at the center, we have our 0. If we move to the right, 1 increment of 1/8, then normally we'd go up 1 here. But in this case, since there's a factor of 3 in front of the function, it's going to be 3 times stretched by a factor of 3 vertically. Our next increment of 1/8 gives us a vertical asymptote. So does that negative 2/8. And then finally, at negative 1/8, we have a y value of negative 3. And so we can graph. And it looks something like this. Ah, that's not that nice looking. My drawing skills are really, really bad right now. All right, well, that's close enough. Okay, so let's graph it actually on decimals. Why not? 3 tangent 2 pi x. 3 tangent 2 pi x. No, you put the pi in there. 2 pi x. Okay, and then, whoa, that's a lot of stuff there. Let's see here. And we graphed from x equals negative 2 pi over 8, I believe, to positive x equals 2 pi over 8. Is that what we did there? Let me double check. Oh, not 2 pi over 8, but negative 2 over 8 and positive 2 over 8. Let me take off that pi there. There we go. And that looks like one period. There's our vertical asymptotes in green and purple. And this is what we graphed. Does that look like my graph? Yeah, close enough. It's just a sketch. All right, very good. Yeah, it looks a little bit wonky there. But if I was a little bit better at graphing here, or a little bit smoother here, I'm kind of not working on a desk right now. It would look, a little curvy, nice and smooth like that. Something like that. Meh. All right. All right, let's go ahead and give the last example here. This is kind of a cool example, and there's some cool examples in the worksheet. So read those, understand what they're talking about. But basically, trig functions can model different things in the real world. And these are things that naturally occur. So it's pretty nice. In this case, let's go ahead and read. It says sinusoidal models. The sine and cosine functions are of great importance to meteorological studies, as when modeling the temperature based on the time of day, the illumination of the moon as it goes through its phases, or even the prediction of tidal motion. All right, well, that's pretty cool. 3 different applications there. Number 63 says, the graph given shows the deviation from the average daily temperature for the hours of a given day, with t equals 0 corresponding to 6 a.m. A, use the graph to determine the related equation. Okay, we've already done some of that. B, use the equation to find the deviation at t equals 11, which is 5 p.m., and confirm that this point is on the graph. And then C, if the average temperature for this day was 72 degrees, what was the temperature at midnight? Okay, cool. All right, this is nice. This is a nice problem. So 3 different parts. So first of all, part A, it says use the graph to determine the related equation. All right, oh, and this is a nice one here because we are starting here at a negative value. So what function might this be here? And I'll give you a moment to think about it. What function do you think this is? So for part A, we can say y equals, hopefully you're thinking of a cosine function. The main thing here is that there's going to be a negative, right? Because cosine usually starts at its maximum. This thing is flipped around. So that means that there's a negative in front of the function. The amplitude, it looks like, this distance here is 4 units. And so that tells us that A is equal to -4. We already put the negative there, so we'll just say A is 4. So y equals -4 cosine of, and then we need to figure out what B is. Remember that we said a period is equal to 2 pi divided by B, but then we have to figure out, well, how long is a period here? A period here, we can see from start to finish, it finishes one cycle in 24 units, in this case 24 hours. And so B is going to be what? If we divide by 24 at the same time, the B's cancel, we divide by 24, and so we get that B is equal to 2 pi over 24, or pi over 12. So pi over 12 x. And actually, since this axis here is labeled as a t, we'll put a t there. And so instead of calling it y, let me call it f of t, just to give the a little more explicitly there that it's a function of time t. So there's part A. Use the equation to find the deviation at t equals 11. So let's go ahead and plug in t equals 11. And so basically for part B, we want to find f of 11. And this is -4 cosine of pi over 12 times 11. Now, this is -4 times the cosine of 11 pi over 12. If we don't have a calculator, I can't punch that into the calculator. And so it tells us that this is at t equals 5 p.m. Okay, so if this is, notice that it says t equals 0 is 6 a.m. So then we just need to kind of count and say, okay, well, use my green. This is 6 a.m. I'll put vertical bars. 7 a.m., 8 a.m., 9 a.m. Oops. Let's see here. This is counting by twos, right? Let me back up for a moment. Yeah, and it's a good idea to keep in mind the scaling of these axes. The horizontal axis, it looks like it's going by twos. So we still start t equals 0. It is 6 a.m. here. So we'll count by twos though. 7, 8 a.m., 9, 10 a.m., 11, 12 p.m., 1, 2 p.m., 3, 4 p.m., and then so 6 p.m. here is at 12, which makes sense. 6 p.m. is 12 hours later than 6 a.m. And so we wanted 5 p.m. So here we go. I'll draw a big tick mark. And we can see that the deviation is right there. It says use the equation to find the deviation at t equals 11, 5 p.m. and confirm that this point is on the graph. So let's actually use, I know we don't have calculators allowed on the worksheet, but since this is a textbook problem, that's why it's kind of giving us a problem that we can't completely solve without a calculator. But we can see that the value when t is equal to 11 is somewhere around, maybe more than around 3. Looks like more than 3. So let's find -4 times the cosine of 11 pi over 12. Let's see if we can do that here on one of our apps here. No, I don't know if that is. Okay, sure. Let's see. So 11 pi over 12. Okay, we hit enter. And then let's take the cosine of that. And what is this here? What's going on there? Okay, let's try again. Cosine. Cosine of 11 pi over 12. Those parentheses, 2.8. So around 3. Yeah. 2.879. That means I must have drawn my line a little crooked. Yeah, I mean, I can believe that. Maybe the graph is just slightly off there. Ah, let's see, I'm not 100% experienced with this app here. Here we go. Yeah, so when I multiply by that cosine function value by -4, So that cosine, that cosine value by -4, we do actually get, what do we get here? 3.8637. And so if we double check the graph again, 3.86, whatever that was, 3.867. And I'm seeing here, it looks like I might have even marked it wrong here on this chart. Yeah, t equals 11 is actually right here. I'll mark it in red. And this makes a lot more sense. Here's our point. It's almost 4, 3.86. So very good. Through double checking with the calculator, we're able to see that. I marked it in the wrong spot. All right, so everything is correct there. We use the equation, and then we confirm that this point is on the graph. And then finally, part C, if the average temperature for this day was 72 degrees, what was the temperature at midnight? Okay, so if we were at 5 p.m. on that red mark, then at 12, this is 6 p.m. 2 hours later would be 8 p.m. 2 hours later would be 10 p.m. And we wanted the temperature at midnight, so that would be the next 2 hour mark. Oh, so at 12 a.m., what is the temperature? Now remember that this measures deviation from the average temperature. Deviation from the average daily temperature. And so 72 degrees is the average. Since this is on the x-axis, the value of this deviation is 0. That means that we are exactly at 72 degrees. So 0 or no deviation from the average. All right. And so then for part C, we can say at 12 a.m., there is 0 deviation from the average temperature of 72 degrees. So it is 72 degrees Fahrenheit. All right. Cool. All right. And so they use this kind of stuff. You watch the morning news, they give you the temperature, they tell you, well, I know the person that I watch every morning says, oh, we are 4 degrees colder than it was yesterday. So they're checking the deviation from, the previous day. And sometimes they'll say, oh, this is 8 degrees hotter than the average temperature, or the average temperature is this temperature. And so, they keep track of all this stuff. All right. And then I think we all know that the deviation in temperature, yeah, let's say at 6 a.m., it's cold. And then as the sun comes up, it starts to warm up, reach the average temperature, and then it starts to kind of get warm throughout the day. But then the sun starts to set and the temperature starts to drop. And then the sun comes out again, that starts to rise and so on. Right. So just a kind of cool application of trig functions there. All right. So sorry this video was so long and I made a couple mistakes there. I think I caught them all though, so we corrected them. So everything is all, good. Yeah. So if you have any questions, feel free to maybe leave a comment or something. Let me know what your question is, or obviously you can come into my office hours and ask if you're in my class. Okay, so hope that video was kind of helpful. We did have to rush through some of the stuff. There's way more that we could say, but as always, we don't have time to say it all. So So I wanted to make this video here just to give a little bit more background than what we might be able to give in class. All right, well, I will see you in the next video. There will be one more video going over inverse trig functions. And actually that really depends on these graphs here. In a sense, it's going to depend on these graphs. So we need to learn these graphs well so that when that inverse trig function stuff comes up, you know, you can kind of understand why the domain and range of those trig functions are what they are, or those inverse trig functions. All right, so I'll see you in the next video. Thanks for watching this one.